All right, so today is our third session for our Algebra 1 Regents review, okay? My name is Mr. Ken Olympio, call me Mr. Olympio, Ken, no big deal, okay? So a couple topics that we're going to discuss today are relations and functions, special functions, operations on functions, compositions and inverses of functions, transformations of functions, sequences, both arithmetic and geometric, displaying and interpreting data. So a lot of stuff dealing with functions today, okay? So relations and functions, a couple things that we need to know. The first thing is any set of ordered pairs is said to be a relation, meaning if we have any sort of an x value and a y value on our graph, it's said to be a relation, okay? Another thing, a couple things to keep in mind is our first set of coordinates that we're going to have in each ordered pair is going to be our domain. So all of our x values when dealing with graphs are going to be our domain, and our second coordinates or our y values are going to be considered to be our ranges, okay? So here 1, 2, and 3 is the domain, 2, 4, and 6 is the range of our relation. So if we're given our ordered pair right up top, all of our x values 1, 2, and 3 are going to be our domain, and our y values 2, 4, and 6 will be our ranges. Now function. A function is a well-defined relation between two sets. So say A and B, in which every element of A has a unique image in B. It's denoted by F is A to B, okay? So when we're dealing with functions, a function is said to be one-to-one, meaning every x value has one y value, okay? Now, have you guys learned this stuff before already? Yeah. Okay, cool. So vertical line test. Vertical line test is exactly what it says it is. So if we're given a graph, okay, and we're given a function on our graph, since no two ordered pairs of a function can have the same first element, it means that a vertical line is going to pass through any part of the graph and can intersect the graph only once. So if we were to do the vertical line test on our graph over here, we'd notice it would pass through 1, 2, 3 different points. So in this scenario, it would not pass our vertical line test, meaning it's not a function. For a horizontal line test, once again, it's very self-explanatory. If a horizontal line passes through the graph of a function only once, it means that each range element, our y value, has a unique pre-image x, and the function is one-to-one. So, in our second graph over here, if we did the vertical line test, it would also pass. If we happen to do the horizontal line test, it would also pass, meaning that we have a one-to-one function. Our x value has one y value. So we have a question here, which representations are functions? So I'll give you guys about a minute or so to start working on these. So take a look at each of our choices. Okay, we have our x values and y values. In choice 2, we have a set of ordered pairs. Set 3, we have a graph. And set 4, we're given y equals 2x plus 1. So take about a minute or so, okay, and which one do we think would represent a function? Yeah, absolutely.
2 and 4.
2 and 4? Perfect. So if we have, okay, our choice 1 is not a function. So when x equals 2, there's 2 values for y. So if we see when x equals 2, we have a value of y, which is 6. And then on the second one over here, when x equals 2, we have a value of negative 6. So we can definitely rule that one out. If we go to choice 3, okay. If we check out choice 3, this wouldn't be a function because if we did the vertical line test, it would pass through 2 points. Choice 2 and choice 4, for choice 2, every x value has a y value. And for choice 4, our linear function is in y equals mx plus b. So our correct answer would be, there we go, choice B, which is 2 and 4. Very good. Now, function notation. So there's a couple different ways we can go about doing this. So the first one, okay, our first one is going to be a set of ordered pairs, meaning once again, our set of our x values and y values. So if we have let A to equal 0, 1, 2, 3, and B to equal 5, 6, 7, 8, every A value is going to equal a B value, or every X value is going to equal a Y value. we notice that where f maps x to be x plus 5, meaning adding 5 to each of our x values, adding 5 to each of our x values will get me my y value. So if we use an arrow diagram, we put all of our x values on the left-hand side, we'll put all of our y values on the right-hand side. And simply just draw arrows showing each x value has a y value. Now if we were to have two arrows coming out, come on in, join the fun. If we were to have two arrows coming out of one of our numbers, meaning 2 would, let's say, had an arrow going to 6 and 7, we would know it's not a function, because that means we have two y values to one x value. So, our next question is, Faith wants to use the formula C of f equals 5 over 9 times f minus 32 to convert degrees Fahrenheit, which is our f, to degrees Celsius. If Faith calculated C 68, what would her result be? Okay, so take a second or so and let's see if we can come up with an answer for this one. So the way we would actually set this problem up, okay, is plug in our 68, okay, plug in our 68 for our f value, okay. So if we plug in 68 for our f value and solve, we notice that our answer is going to be B. So if we had 5 over 9 distributed across to our 68 minus 32, which would be 36, 5 over 9 times 36 is going to get me to 20, which our correct answer is going to be choice B. Okay? Any questions so far? Yes?
Wouldn't you try to be ahead because you're converting?
Oh, sorry. It should be Celsius. Whoops. Should be A. Apologize. Not B. Okay? Good. Now, absolute value. Have you guys dealt with that absolute value before? Okay. So we know that when dealing with absolute value, we're always going to end up with positive answers. Okay. I always have a problem with this board. There it is. Okay. So, absolute value function is f of x equals our absolute value bars of x. Denoted can be defined algebraically in two different ways. Okay. So our first way for x, okay, we're going to have x is greater than or equal to 0. For our second way, we're going to have negative x, where x is going to be less than 0, because we know that whether we have a positive or a negative inside our absolute value bars, our answer is going to be positive. So for our domain, our x values, they're going to be all real numbers. For our range, which is our y values, all non-negative real numbers. Second definition that we have here of the absolute value of x is going to be the square root of x squared. So if we have our example here, this is solve for x, and we have the absolute value of x minus 1 plus 5 equals 0. The two ways we would solve it algebraically, we would set it up as x minus 1 to equal 5. Okay, solve for x, we get x to equal negative 4. If we were to solve it the second way algebraically, meaning we have to come up with a negative 1 to distribute across to our absolute value, it would be negative 1 times x minus 1 to equal negative 5. Solve algebraically, we solve for x, we'll find that our second solution is going to be x equals 6. So if we were going to solve this graphically, we're looking for a point x whose distance from the point positive 1 is 5 units. So if we move 5 units to the right, we're going to end up with positive 6. Now, if we end up going 5 units to the left from positive 1, we're going to end up with a negative 4. So hence, once again, our solution is going to be x is going to equal positive 6 or x is going to equal negative 4. So if we plugged in a positive 6 or negative 4 into our original equation, we'll get the right answer. We'll get the same answer. Okay? So our example we have here is the graphs of the function f of x is equal to the absolute value of x minus 3 plus 1 and g of x equals 2x plus 1 are drawn. Which statement about these functions is true? So take another minute or so, okay, and see what solution we can come up with here. So what did we come up with as our answer? Choice B, right? So what we ended up doing is we had our set f of x to equal our g of x. So we set up as absolute value of x minus 3 plus 1 to equal 2x plus 1. Solve algebraically, you subtract the 1 on both sides to be left with absolute value of x minus 3 to equal 2x. Now when we solve for our two values of x, when we have x is greater than or equal to 3, and we solve, we'll get x to equal negative 3, which contradicts our assumption of x is greater than or less than 3. If we have x is less than 3 and solve it, we're going to end up getting with our x equals 1. So therefore, f of x equals g of x when x equals 1. So choice B is correct. Linear functions. So we talked a lot about linear functions in our second session, okay? So there's a couple different things that we have to keep in mind, or different forms of linear functions. So the first one we have is our slope-intercept form, which we know is y equals mx plus c, okay? Or some people say it as y equals mx plus b. We know our m. Our m value is going to be our slope, okay? Our m value is going to be our slope, and our c or our b value is going to be our y-intercept. We also have our point slope form, which is y minus y1 equals m times x minus x1, where the x1 and y1 is any point on the line, and the m is still going to be our slope. Our intercept form in the top right we have is x over a plus y over b, which equals 1, where our x1 and y1 and our x2 and y2 are the points on the line. And then we have our 2-point form, where it's y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1, where once again, our x1, y1, and x2 and y2 are the points on the line. So if we're given this example, the table below shows the values of 4 different functions for given values of x. Which table represents a linear function? Okay? So if we were to look at this example, we're trying to look for a pattern, right? We're trying to look for our pattern in our y values. So if we start across over here, from 12 to 19, okay, we add 7. From 19 to 26, we add 7. And from 26 to 33, we add 7. So right off the bat, we know that our first choice is going to be a linear function. Okay, because we have a pattern in our y values. They're each increasing by positive 7. If we go to our second choice, we got negative 1 to positive 1, which would be plus 2. 1 to 5, which would get me plus 4. And then 5 to 13, okay, would get me my plus 8, okay? So there's no pattern here, okay, except for the fact that start off with 2, if we double 2 we get 4, if we double 4 we get 8, okay? This would not be a linear function. Come across to our third choice, add 3 from 9 to 12, from 12 to 17 we add 5, and then from 17 to 24 we add 7. So once again, okay, we're increasing every single number by plus 2. So we have a plus 3, add 2 to it to get me my plus 5, add 2 to that to get me to my plus 7. Our last choice we have negative 2 to a positive 4, okay, which is going to be plus 6. 4 to 14, which is going to get me my plus 10. 14 to 28, which is going to be plus 14. So we know that this also isn't a linear function. So the answer that we would have for our question, which table represents a linear function, is going to be choice A, f of x. Okay? Any questions so far? Now let's talk about greatest integer functions. Okay, greatest integer functions. Greatest integer function maps every real number x onto the greatest integer whose value is less than or equal to x. Hence the domain of this function is all real numbers, but the range is only integers. So, if we look at our table over here, and we look at all of our data on the left-hand side, if we have negative 2 for negative 2 is less than or equal to x, which is less than to negative 1, and we plot our dot, plot our point, okay, we notice that our negative 2, okay, our x value is going to be greater than or equal to negative 2, which is going to be less than or equal to for negative 1. If we use negative 1 for negative 1 is less than or equal to x, which is less than 0, okay, so on and so forth, you notice that our plots on our graph are going to look sort of like a diagonal, and each have a relation to each other, okay? Now, if Morgan could start wrestling at age 5 in Division 1, he remains in that division until his next odd birthday when he was required to move up to the next division level. Which graph correctly represents this function? Okay, so take about 30 seconds or so and try to figure out which graph would represent this function the best. So if you look at choice 2 and 4, you could easily eliminate those. You could eliminate those because when he is age 5 in Division 1, they don't even have the plot pointed. So we could quickly eliminate choice 2 and choice 4. If you jump to choice 3, okay, we have an issue because at age 7 they have him listed in 2 different divisions. They have him listed in the first division and the second division. Same thing at age 9, age 11, and 13. So we would eliminate choice 3 as well. Choice 1, which would be our correct answer, you notice that when he turns to age 7, he drops out of his first division and moves up to the second division. So on and so forth when he turns 9, 11, 13, and 15, he's increasing his divisions. Quadratic functions. So a quadratic function, okay, we also talked about in session 2, is ax squared plus bx plus c, where a does not equal 0. So when we plot the graph of a quadratic function, the resulting figure is called a parabola. The turning point of the parabola is called our vertex. So our vertex is going to be our highest or lowest point on our parabola, represented by our maximum or minimum value. So the example we have here is the distance covered by a train in feet after t seconds is given in the form of quadratic function. f of t equals 25t squared plus 5t plus 4. Find the distance covered by a train after 1 minute. Okay? So our t represented in our quadratic function here is going to be our seconds. So we need to know how far the distance of the train could go after 1 minute. So we know 1 minute is going to equal 60 seconds. So all we have to do is plug in 60 for wherever that we see t. So now we have f of 60 equals 25 times 60, this should be squared, plus 5 times 60 plus 4, and solve, and we get 90,304. So hence the train is traveling at 90,304 feet after 1 minute. Okay? So I have a little video for you guys here.
We're going to learn about the turning point or vertex of a quadratic equation. The turning point or vertex is the point where the direction of the graph changes. That is, if the graph was decreasing, the direction changes to increasing. Or, if the direction was increasing, it changes to decreasing. Let's look at an example. Find the turning point of the parabola given by the equation y equals x squared minus 4x plus 3. First, graph the given equation. Here's the graph. The axis of symmetry is x equals 2. Notice that the vertex lies on the axis of symmetry. The point of intersection of the axis of symmetry and the parabola is the point 2, negative 1. Therefore, the parabola changes direction from decreasing to increasing at 2, negative 1. So now, you know about the vertex of a quadratic equation.
So for our example here, we have which equation, an ordered pair, represents correct vertex form and vertex for j of x equals x squared minus 12x plus 7. So take about a minute or so and see what answer we could come up with here. So our answer is actually going to be choice C. Okay, choice C meaning j of x equals x minus 6 squared minus 29, where our x value is going to be 6 and our y value is going to be negative 29. So if we have j of x equals x squared minus 12x plus 7, okay, and we'd come down to x squared minus 12x plus 36 plus 7 minus 36, and we factored it out, we would be left with x minus 6 squared minus 29, meaning our vertex or our turning point of our parabola is going to turn at x equals 6 and y equals negative 29. Okay? So all we did was basically do the steps backward of FOIL method. Okay? Polynomial and rational functions. So a polynomial function is a function which maps our r to r. It is in the form of f of x equals a0 plus a1 times x plus a2 times x squared plus a3 times x cubed, so on and so forth, okay? Plus a to the an times x to the n power, where n is the continuing number, okay? So the highest value of exponent n is called the degree of the polynomial. So if we're given the function 2x to the 4th plus 3x to the 3rd minus 5x squared plus 1 is a polynomial function with a degree of 4. Okay, a degree of 4. A rational function is a function in the form of f of x over g of x, where f of x and g of x are polynomial functions as defined above, where g of x does not equal 0. So the example we have down low is x squared minus 2x minus 1 over 2x plus 1, where x does not equal 1 over 2. Okay? So if we have our question here, okay, we're given our graph, which equations represented the graph above? Okay? So what you really want to look for here, okay, is where your lines are crossing through your x-axis. So if you see it's crossing through a -2, it crosses through a +1 and a +3, which equation, okay, knowing this information of where it's crossing our x-axis, knowing this information, which equation is going to represent our graph above the best, okay? So if we looked at our answer here, our roots of our equation, we know are -2, +1, and +3. So we know that if x equals -2 is a root, then x plus 2 is a factor. If x equals 1 is a root, then x minus 1 is going to be a factor. If x equals 3 is a root, then x minus 3 is a factor. So our equation that we're going to have is y equals x plus 2 times x minus 1 times x minus 3, okay? We'd be left with x plus 2 times x squared minus 4x plus 3, or if you use the FOIL method here, we'd be left with x minus 3 times x squared plus x minus 2, or do the FOIL method using x minus 3 and x plus 2, we'd be left with x minus 1 times x squared minus x minus 6. So among these three given choices, the only correct equation is choice 2, okay? Choice 2, which on our answers over here is choice B, okay? So once we find the roots of the equation and we set up our parentheses as our factors, all we do is we multiply each set of parentheses to each other and we find out which equation works best or which equation is given to us as an answer. Any questions so far? Exponential functions. Now, exponential functions, there's two types that we're going to be working with. We're going to have exponential growth and we're going to have exponential decay. Now, exponential growth is going to be represented as p times 1 plus r over 100 being raised to n. So our n is actually going to be our time, okay? And our r is going to be our rate. Our rate is always going to be given to us as a percentage. Every single time we get a percentage, we want to change it to a decimal. So we move our decimal 2 places to the left. Okay, so in our example, we have Jenny invest $5,000 in a savings account. The compounded rate of interest is 10%. Find the amount she received at the end of 5 years. So our P, okay, our P is going to be represented as our initial amount, what she started off with, what she initially invested. So she initially invested $5,000, okay? And the compound rate is 10%. So what we're going to have it as is 5,000 times 1 plus 10 over 100 or 0.10. And we want to know how much he's going to make over 5 years. So our n is going to be our time, raised to the 5th power. So now we're left with 5,000 times 11 over 10 being raised to the 5th power. And we find out that once we solve, we'll get $8,052.55 after 5 years. So our P is going to be our initial amount that she invested, 5,000. Our R is going to be our rate, which is 10%, okay? And then our N is going to be our time, which is 5 years. So all we have to do is when we're looking at this example, okay, is find out which amount and which number plugs into where in our equation. So the table below represents a function f. The equation that represents this function is what? So let's take a couple seconds to work on this. Let's see, having our x values of 3, 4, 6, 7, and 8, and our f of x values is 9, 17, 65, 129, and 257. Let's see which equation represents the function best. Okay? Let's see what we can come up with here. So what do we come up with for an answer?
D.
You say choice D?
Yeah.
Okay, so what'd you do for choice D?
I plug in like the values for like the exponent.
Okay. And then the y value for your f of x value?
Oh, wait, sorry. No, that's right, actually.
That's all right. So what you want to do is wherever you see your x, you want to plug in your x values, and it should equal your f of x value, which is in this scenario going to be our y values. Okay. So if we did that, the answer we should come up with would be choice C. Okay. So if we use our ordered pair 3, 9, okay, we have 9 to equal 2 to the third power, which is our x value, plus 1, we notice that it checks out where 9 equals 9. Okay, if we use all of our ordered pairs, 4, 17, 6, 65, 7, 129, 8, 257, and plugged in our numbers, okay, as our x value and then our y value, we notice that each of our points, each of our ordered pairs will check out. So the correct answer we're going to have is going to be choice C. F of x equals 2 raised to the x power plus 1. Okay. Questions so far on anything that we've gone over? Okay. Piecewise defined functions. Now, a function defined in such a way that one rule doesn't describe the behavior behavior of the function over its entire domain. So the example we have here of f of x is x squared if x is less than 0, 1 if x equals 0, and then 2 times x plus 1, or 2x plus 2, if x is greater than 0, is called piecewise defined. Okay? So if we see our graph, okay, if we plot our points and we plot our graph right here where x squared, we start at our origin and it'll raise up, okay, and we plot our point 1, which we see right here, and our point 2 times x plus 1, all right, we notice that our graph over here is going to be called piecewise defined. Since there's a jump at x equals 0, we could say that the graph is not continuous at x equals 0. So only one of our lines, only one of our equations comes out of our origin. The other two equations do not come out at 0, so therefore it's not continuous. Not continuous. The signum function is a special, okay, piecewise defined function, meaning if we have 1 if x is greater than 0, 0 if x is equal to 0, and -1 where x is less than 0. Our domain is all of our real numbers, and our range is going to be -1, 0, and 1. The graph of the signum function is as followed. Okay, so we notice that at point 1, okay, our point 1, we have our line that cuts through our y-axis. At point -1, our line cuts through our y-axis, and then obviously at 0, our origin, starts right in the middle. So this would be a signum function, okay? Now, the question we have here is a function is graphed on the set of the axes below, okay? So which function is related to the graph? So let's take a look at all of our choices and let's see which one of our functions would make this graph happen, okay? So let's see what we can come up with here. So let's take a look at this. If we have our first piece, okay, where x is less than 1 is the parabola of y equals x squared, okay? So x is less than 1, the parabola is going to be y equals x squared, okay? The second piece, where x is greater than 1, is a line with the slope of 1 over 2, passing through the point 3, 2. Okay, so it's passing through our point here, all right? So its equation is going to be y minus 2 equals 1/2 times x minus 3. Y minus 2 is going to equal 1/2 x minus 3 over 2. Add 2 to both sides. We're left with y to equal 1/2 x plus 1/2. Therefore, f of x is going to be x squared, where x is less than 1, okay, where our y is x squared, and we're left with 1/2 x plus 1/2, where x is going to be greater than 1. So the correct answer that we have for this example would be choice B. Choice B. Now, arithmetic operations and functions, okay? So given two functions, f of x and g of x, we have 4 different types. We have addition, subtraction, multiplication, and division, okay? So each one is as followed, okay? If we have f plus g for addition, all right, our domain of f plus g is going to equal domain f, okay? Does everybody know what this is? What this symbol is? Nobody? Intersection, okay? It's an intersection symbol, okay? Intersection of domain G. Our subtraction would be f minus g, okay, where f minus g is going to equal our domain f intersecting our domain g, okay. Multiplication, f times g, is obviously going to be f times g equals the domain f intersecting domain g, and division is going to be f over g equals domain f intersecting domain g, okay. So suppose f of x equals 2x plus 7 and g of x equals minus x plus 2 equals a negative x plus 2. We have domain f intersecting domain g to equal r. So if we did f plus g, meaning 2 plus 7 plus negative x plus 2, we get an equation of x plus 9. If we were to do our subtraction, 2x plus 7 minus negative x plus 2, we get 3x plus 5. If we were to do g minus f, okay, for subtraction we have to set it up both ways. We have to have our domain f first, and then we have to have our domain g first. We get negative x plus 2 minus 2x plus 7 to get a negative 3x minus 5. And then we have f times g, which would be 2x plus 7 times negative x plus 2, which would get me negative 2x squared plus 3x plus 14. And for our division, we have f over g, which would equal 2x plus 7 over negative x plus 2. For x to not equal 2, and g over f is going to be negative x plus 2 over 2x plus 7, where x does not equal negative 7 over 2. Okay? So all we're doing for all 4 of our steps is we're following addition, subtraction, multiplication, and division of each problem of each of our function, and we're either going to add them together, subtract them together, divide them together, multiply them together to get our different equations. Composition of functions. So given 2 functions, f of x and g of x, f composed with g denoted f times g means f times g of x. In other words, our g of x is substituted for x in the formula for f. Okay? So what we're doing is we're replacing our g of x for x when we're trying to solve for f. So suppose we have our same 2 equations, 2x plus 7 and negative x plus 2. Domain f equals domain g. We have f times g of x to equal f times g of x. We do 2 times negative x plus 2 plus 7. So all we did here, okay, all we really do here is we're taking our g of x equation and we're plugging that in for our x value. So now we have, which is 2x, which is now going to be 2 times negative x plus 2 plus 7, and solve that way. So we'll be left with negative 2x plus 4 plus 7, combine our like terms to get negative 2x plus 11. Okay? Now we have to do it the other way. We have to plug in our f of x equation for our x and our g of x equation. So what we do here now is if we have negative x plus 2, plug in our 2x plus 7 for our negative x, so we'll have a negative 2x plus 7 plus 2. Distribute your negative 1 across, you're left with negative 2x minus 7 plus 2. Combine your like terms, you're left with a negative 2x minus 5. So this is very similar to what we talked about in session 2 with the substitution method of solving algebraically. So substitute your first equation, okay? Substitute your x value into your x value of your second equation, and vice versa.
This animation illustrates how the composition of 2 functions takes place. Let us take an apple and place it on a cutting device or machine. It is cut into pieces. These pieces are then fed into another machine or mixer. The mixer crushes the apple pieces and turns them into a puree or juice. So, in the process, an apple is converted into apple juice. The apple can be thought of as the input, the cutting device as the function f, and the apple pieces as the output for the function f. Now, these same apple pieces become the input for the mixer, which we'll call function g. The final product, the juice, is the output for the function g, and also for the entire process. So, under the action of the composite function g, composition f, an apple is transformed into its juice. Mathematically speaking, suppose a number x is fed into a machine f, which squares the value of x. Then the number x squared is fed into another machine, g, which adds 10. That is, g, composition f, is x squared plus 10. If x assumes the values of 1, 2, 3, etc., we finally get g of f of 1 equals 11, g of f of 2 equals 14, g of f of x equals 19, and so on. What happens if the order of the functions are reversed? That is, find f of g of x. Why not try the problem and see? Let's look at an example of a composition of 2 functions. Let f of x be defined as x squared and g of x be defined as x plus 10. To find g of f of x, we feed the value of 4 into the equation for f of x. 4 becomes 16. Substituting the value of 16 into g of x, we get 16 plus 10, or 26. This process is written as g dot f of x and is equal to g of f of x. So, g of x squared becomes x squared plus 10. G of f of x is called a composite function.
Okay, so what we're going to talk about now is multiple transformations of a function. Okay? The order in which transformations should be performed upon a prototype or basic function are as follows. So there's 4 types. We have horizontal translation, we have dilation, which means we're either going to stretch it or we're going to shrink it. We have reflection, and we have vertical translation. So if we're given this, this function, graph the function f of x to equal x plus 2 squared minus 4, okay? So if we graphed x plus 2x minus 4, we notice our red parabola right here, okay? Right here. Our solution, okay, the prototype graph is g of x to equal x squared. So if we were to just graph x squared, okay, our parabola is as followed with our blue line. So step 1, translate the graph 2 units to the left. So if we move it 2 units to the left, we're given, okay, our green parabola, which is x plus 2 raised to the 2nd power. Step 2 is translate the graph 4 units downward. So if I go 4 units downward from my green parabola, we notice that we land exactly on our main parabola, which was x plus 2 squared minus 4. So how does the graph f of x equal 3 times x minus 2 squared plus 1 compared to the graph of g of x equals x squared? So if you were to graph both of these, okay, if you were to graph these, what is the relation? How do they compare to each other? So I'll give you guys about a minute or so and let's see what we can come up with. Gotcha. I'll give you guys a little hint. When we have a 3 on the outside of our parentheses here, okay, that's actually going to make the graph a little steeper. Okay, that'll be a little steeper. So what do we come up with as an answer? What do we got? Choice B? Very good. Choice B. The graph of f of x is going to be narrower than the graph of g of x. And its vertex is moved to the right 2 units and up 1 unit. So, if we were to graph g of x equals x squared, our vertex is going to be 0, 0. Our parabola is going to cut through, or it's going to be lowest at 0, 0. If we were to graph f of x to equal 3 times x minus 2 squared plus 1, we know our plus 1, it's going to shift my graph up 1 unit, and it's going to shift the graph 2 units to the right, and with our 3, it's going to actually narrow the original graph 3 times steeper. Okay, so therefore, it narrows the vertex and is shifted 2 units to the right and up 1 unit. That means our choice B is going to be our correct answer. So that's how our 2 g of x and f of x will compare to each other. Inverse functions. Inverse functions are exactly what they are. You just find the inverse, you find the opposite. So the function f, a to b, is said to be 1 to 1 if no 2 elements in b have the same pre-image in a. So that is f of x of 1 equals f of x2 if and only if x1 is equal to x2. So consider the function. We have -1, -3, 0, 0, 1, 5, and 3, 7. This function is 1 to 1. If we reverse the ordered pairs of the function, a new function is formed. This function is called the inverse of the original function, denoted as f to the -1. So in this example, f to the -1, all we're doing is we're reversing our ranges and our domains. So if we change -3 to 1, we're left with -3, 1, still 0, 0. Switch your 5 and 1 to get 5, 1, and switch your 3 and 7 to get 7, 3. So find the inverse function of y equals f of x to equal x minus 5 over 2. Sketch the graph of f and f to the -1 on the same coordinates. So what we're going to do is, since the inverse of the function is formed by reversing the ordered pairs, we could find the inverse by interchanging x and y. So this is now going to give us x equals y minus 5 over 2. However, we wish to express our function as functions of x, not as functions of y. So now we have to solve that equation. The way we would solve this equation would be x to equal y minus 5 over 2 to now equal y equals x plus 5 over 2. So all we did with our inverse is we change our signs from subtraction to addition, and we change our x value and our y value. So whenever we're dealing with inverse functions, okay, we just replace it with our opposite function. Okay, so you just do a flip-flop, that's all it is. So graphing y equals x minus 5 over 2 and its inverse y equals x plus 5 over 2 on the same axes, we can see that function and its inverse were reflections of each other in the line y equals x, also known as the identity line. So if you notice right here, our blue line is going to be our y equals x plus 5 over 2, and then our red line is going to be y equals x minus 5 over 2. So a composition of a function with its inverse produces the identity. So if we have our function of y equals 1 over x, the inverse is going to be y equals 1 over x. So f of f to the -1 is going to be x. Same thing, if we had y to equal x, the inverse is still going to be y to equal x, which is still going to give me f of f to equal x. Does everybody see where I'm going with on this one now? Very good. Okay? So let's do this example and then we'll take a quick break. So we are given f of -1x equals -3 over 4x plus 2. Which equation represents f of x? Okay? So let's take about 45 seconds or so and let's see what we can come up with on this answer. So for our answer, if we have f to the -1 of x to equal -3 over 4x plus 2, we replace our x with our y, it's going to get us as y equals -3 over 4x plus 2. To find the inverse, okay, to find the inverse of f to the -1 of x, or f of x, let's interchange x and y in the above equation and solve for y. Okay? So if we have x to equal -3 over 4y plus 2, and we start solving, we subtract 2 on both sides to get x minus 2 equals -3 over 4y. We're going to be left with y to equal -4 over 3 times x minus 2, or y to equal -4 over 3x plus 8 over 3. So the correct answer we're going to get for this one is going to be choice B. Choice B. Any questions so far? All right, so we're going to take about a 5 or 10 minute break for you guys to kind of stretch your legs and stretch your arms out, and then we'll come back for the second part of session 3. If If you guys also ever have any questions, you could always go to learnamerica.com. There's practice tests there, okay? Practice examples and videos of the sessions and everything. So if you guys ever want more practice, if you go to learnamerica.com, there's tons of examples, tons of practice exams and tests there as well. All right, so like I said, we'll regroup in about 5-10 minutes or so, all right? Cool. All right, so welcome back. We're gonna do our second part of our third session here. We're gonna start off with finite sequences, okay? So a sequence of numbers is ordered. We're gonna use parentheses to denote sequences and braces or brackets to denote sets. So if we change the order, we change the sequence. So the sequence we have is 0, 1, 8, 27 is not the same as 27, 8, 0, and 1. So you have to keep it in the same order. Each member of the sequence is assigned a specific position. Sometimes mathematicians name a sequence using capital letters, so they could refer to it without having to list the entire sequence. The number in the sequence is called terms. So all the numbers that are in your sequence are going to be called terms. The number of terms is the length of the sequence. So the even numbers between -5 and +5, written in increasing order form for a sequence, is going to be -4, -2, 0, 2, 4. So the sequence T, okay, notice as they labeled it with a capital letter, has 5 terms. Hence its length is 5. Consecutive multiples of 3 from 1 to 30, we have sequence S to be 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. So our sequence S is going to have 10 terms, so hence the length of it is 10. So all you're doing is counting the amount of numbers in your sequence to say how long it is. Sequence is defined by recursive formula. So some sequences are defined recursively, meaning first we're going to be given the first term. Second, show how to use the value of a term to get to the next term. This relationship is used to get to the rest of the terms of the sequence. It's called the recursive relation. So we state the length of the sequence, that is, the number of terms. So let S be the sequence whose first term, S1 is 2. Each term is twice the previous term. So the length of S is 6. So find the sequence of S. So we know we're going to have 6 terms in our sequence, okay? And we're going to start off with 2. So note that the recursion for the sequence S can be written as in an expression as Sn plus 1 to equal 2Sn. So this says that n plus 1 for first term is twice the nth term, meaning the next number, the following number coming after. That is, the second term is twice the first term, the third term is twice the second term, and so on and so forth. So if we started off with 2 as our first term, and we know that each term is twice the previous term, so twice the previous term would be 2 and 2 would be 4, twice the previous term would be 8, 16, 32, 64. So all you're doing is multiplying each term by 2, okay, in order to find your sequence. And we know to stop at 64 because it says the length of S is going to be 6. So we make sure we have 6 numbers in our sequence. So in 2014, the cost to mail a letter was 49 cents for up to 1 ounce. Every additional ounce costs 21 cents. Which recursive function could be used to determine the cost of a 3-ounce letter in cents? Okay, so I'll give you guys about 30 seconds and let's see what equation we could come up with. Okay. So what do we think? Who's gotten an answer here? You say choice D, you say choice A. Okay, so let's see who's right. So if we have the cost to mail a letter was 49 cents up to 1 ounce. So the first ounce, okay, the first ounce, let's say you mail a letter. The first ounce is going to be 49 cents. Okay, so that's going to have us as your A, your first A is going to equal 49 because that's your initial amount. Okay. Every ounce after that is going to be tacked on with a 21-cent cost. Okay? Starting amount A1 is 49 cents for 1 ounce. Up to 2 ounces, A2 is 49 cents plus 21, or A2 minus 1 plus 21. To add up to 3 ounces, A3 is A2 plus 21, or A3 minus 1 equals, A3 minus 1 plus 21. So the general form is going to be AN equals AN minus 1 plus 21. So every additional amount, you're always going to add that 21. Always add that 21. So choice A would be correct for this one. Arithmetic sequences, okay? I'm sure you guys have seen this before too. Sequence for which each term, except for the first, is determined by adding the same number to the previous term in an arithmetic sequence. The so-called common difference is denoted by the letter D. The number of terms, that is the length of the sequence, is denoted by L. First term is denoted by A. So our example we have here is find the arithmetic sequence S for which A equals 1, D equals 3, and L equals 6. So clearly the sequence of S is going to be 1, 4, 7, 10, 13, 16. Okay? Your first term, S1, is we already know is 1, okay? But what you're going to do is do 1 plus 3, which is our D value. Our second term, we know is 4. How did I get that? We did 1 plus 1 times 3, okay? Same thing with the third. S of 3 is 7. How did we get that? We did 1 plus 2 times 3. S4 is going to be 10 because we know 1 plus 3 times 3, and so on and so forth, okay? So you're increasing your number that you're adding, but you're keeping what you're multiplying the same, okay? So we can see the pattern. If we use the variable n to denote the place of each term, we see that Sn equals 1 plus n minus 1 times 3. So we can define the sequence using this formula rather than using a recursive definition. More generally, we have the formula Sn to equal A plus n minus 1 times D. So the diagram below represents the first 3 terms of a sequence. So we have term 1, 2, and 3. Assuming the pattern continues, which formula determines An, the number of shaded squares, in the nth term? So let's take a look at these 3, okay? And let's see if we can figure out which formula is best to use, okay? Now using the patterns, remember your shaded areas, okay? Your shaded squares are going to be to the nth term, okay? Let's see how much they increase each term. Let's see what we can come up with here. So let's see, who knows why I wrote these numbers on top of each of my boxes? Yeah. Perfect, right? It's your term, right? Your term 1 has 12 shaded boxes. Term 2 has 16 shaded boxes, and term 3 has 20 shaded boxes. So you can start to see the pattern there, right? Each one increasing by a certain amount. So, term 1, 1 to 12 shaded boxes. Term 2, 2 to 16 shaded boxes. Term 3, 3 to 20 shaded boxes. So, arithmetic sequence between the difference between terms is 4. We notice that we go from 12 to 16 to 20, it's increasing by 4. So the formula for the nth term is going to be a1 plus n minus 1 times d, where a1 is our first term, and d is the difference, and n is the number of terms. So therefore, a1 plus n minus 1 times d is going to become an equals 12, okay, our first amount of shaded blocks, plus n minus 1 times 4. After distributing your 4 across, you'll be left with 12 plus 4n minus 4. Combine your like terms, you're left with 4n plus 8. Okay? So once again, it's very crucial that we understand what each letter means and where to find each letter in each term. Okay? Geometric sequence. Geometric sequence. Okay? A sequence for which each term except the first is obtained by multiplying the previous term by a given number called a geometric sequence. The given number is a so-called ratio and is denoted by r. Okay? So now we're going to be using the r term. As was the case with the arithmetic sequence, the length of a sequence is denoted by L, and the first term is denoted by A. So our example we have here is find the geometric sequence S for which A equals 1, R equals 3, and L equals 7. So the sequence S is 1, 3, 9, 27, 81, 243, and 729. We have 7 terms. Okay? Our first term, 1, is going to be 1 times 3, raised to the 0 power. Okay? Our second term, 3, we get it from 1 times 3 being raised to the first power. Third term, our 9, comes from 1 times 3 being raised to the second power, and so on and so forth. So all we're doing, okay, all we're doing is we're increasing what our number, our 3, okay, our r term, we're increasing the exponent. So we start from 0 and go down to 3, and that's where our sequence 1, 3, 9, 27, so on and so forth is coming from. So if we use the variable n to denote the place of each term, we see that S of n is going to equal 1 times 3 to the n minus 1. Okay? So more generally, we have the formula Sn equals AR, okay? A times R raised to n minus 1. So now what we're going to be dealing with is being raised to the power, dealing with the exponents. That's what's going to be increasing.
We will now study geometric sequences. Consider the sequence t equals 2, 4, 8, 16, 32, and 64. The first term, t1, equals 2. Furthermore, each term, except the first, is obtained by multiplying the previous term by 2. That is, tn plus 1 equals 2tn. For example, t3 equals 8, and t4 equals 16. So t4 equals 2t3. Finally, the length of t is 6. A geometric sequence has the following 3 characteristics. It has an initial term denoted a. It has a ratio, r, that we multiply any term by in order to obtain the next term. It has a length, which tells us the number of terms. Note that the exponent is 1 less than the number which states the place of the term. For example, the 4th term in AR cubed. So the last term is AR to the L minus 1 power.
To find the geometric sequence t for which a equals 2, r equals 2, and l equals 6, start with 2, then multiply by 2 to get 4, then multiply by 2 to get 8, and so on until we have 6 terms. Namely, 2, 4, 8, 16, 32, and 64.
I can bet that none of you guys expected Finding Nemo to teach you about arithmetic sequences today, right? It's interesting stuff. All right, we have one more video here, though.
We shall study the general term of a geometric sequence. In the sequence t equals 2, 4, 8, 16, and 32, notice the following. The first term, t1 equals 2, which equals 2 times 2 to the 0. Then, the second term, t2 equals 4, which equals 2 times 2 to the first. The third term, t3, equals 8, which is 2 times 2 squared. The fourth term, t4, is 16, which equals 2 times 2 cubed, and t5 equals 32, which equals 2 times 2 to the fourth. In all of these cases, the exponent of 2 is 1 less than the index of the term. We will use the variable a to denote the first term, and we will use the variable n to denote the place of each term. The first term, s1, equals ar to the 0. The second term, s2, equals ar to the first. The third term, s3, equals ar squared. The fourth term, s4, equals ar cubed, and s5 equals ar to the fourth. Then, our sequence can be described by Sn equals ar to the n minus 1 power. Notice that the exponent of r is 1 less than the index n of the term. In the sequence v equals 1, 1/3, 1/9, 1/27, and 1/81st, notice the following. The first term, v1, equals 1 times 1/3 to the 0 power. The second term, v2, equals 1 times 1/3 to the first power. The third term, v3, equals 1 times 1/3 squared. The fourth term, v4, equals 1 times 1/3 cubed, and v5 equals 1 times 1/3 to the fourth power. More generally, vn equals 1 times 1/3 to the n minus 1 power.
Okay, so our example that we have here, Alicia has invented a new app for smartphones that two companies are interested in purchasing for a 2-year contract. So company A offers $10,000 for the first month and will increase the amount each month by $5,000. Company B is offering $500 for the first month and will double their payment each month from the previous month. So monthly payments are made at the end of each month. For which monthly payment will company B's payment first exceed company A's payment? So the question really is if she takes company B, okay, if she ends up going with company B, how many months is it going to take company B in order to exceed the amount of company A? So we're actually going to do this one together. So company A is arithmetic sequence. So for the formula nth term, we're going to have a to 0 plus n minus 1 times d, or 10,000, which was their initial, plus n minus 1 times 5,000. So after the 6th month, okay, our n is going to be what month we're on. After the 6th month, she's going to have $35,000. After the 7th month, they're going to offer $40,000. 8th month, they're going to do $45,000. 9th month, they're going to do $50,000. So company B uses geometric sequence, where our nth term is still going to be the month, and we're going to have 2 being raised to n minus 1. Or our A0 is their initial amount that they're investing, which is $500. So $500 times 2 being raised to n minus 1. So the 6th month would be 500 times 2 being raised to 6 minus 1, or 500 times 2 being raised to 5, which you'll get 16,000. Your 7th month, she's going to get 32,000. Her 8th month, she's going to get 64,000. And then her 9th month, she's going to get 128,000. So therefore, company B's payments first exceed the company's A payment at the 8th month. So choice C would be correct. So if you notice, if she took company A's offer, okay, by the 8th month, she'll be getting $45,000 from company A. If she took company B's offer that uses geometric sequence, she notices that by month 8, it's going to be $64,000, okay? So during the 8th month, that is when the crucial money happens there, okay? So choice C, which would have been 8, would be your answer. Bar and parallel graphs, okay? I'm sure you guys have all worked with bar and parallel graphs before, or at least bar graphs, okay? So bar graphs are generally used to compare a specific property of various objects, such as height of buildings, calories and desserts, yearly amounts of snowfall, and different cities. So I actually always tell my students that when we're dealing with bar graphs or pie charts or line graphs or any of those types of visuals, okay, these are things that you're going to see later on in life, okay, when getting a job, when you all start your own career, okay, and the boss tells you, hey, here's a list of data, do me a favor, make it a little more like presentable. The best way to show it is either some sort of graph, whether it's bar, pie, chart, whatever it may be, okay? So these are very important. So the points to remember, okay? Whenever you're making any sort of graph, you need to have a title, okay? You need to have a title. The second thing, provide names and scales for vertical and horizontal axes. So don't just put numbers on your x-axis and your y-axis, make sure those are labeled as well, whether it be your time, people, months, whatever it is. The third thing, make sure the widths of the bars are equal. Nobody wants sloppy graphs, okay? Nobody wants sloppy graphs. And the last thing, make sure the bars do not touch each other and spacing between them is the same. The only time your bars are going to be touching each other is when you're dealing with histograms, which I believe we get to in this presentation. A parallel graph is a type of bar graph where the bars are shown from high to low, with the highest frequency category on the left and the lowest frequency on the right, okay? So the example we have here is Pineview School has the following games, okay? So here's all the sports and here's all the games that Pineview School has: hockey, baseball, chess, cricket, and tennis. Here's the number of members, okay, of the game. So hockey's got 20 people, baseball 30, chess 15, cricket 25, and tennis 35. So as you notice in our bar graph, okay, most important, we have a title. Okay, our first thing was have a title. So the title was games chosen by members. Our y-axis here is going to be the number of members that we have. Our x-axis here is going to be the games that we have, so, which is for 20 people. Okay, so hockey, 20 people. Also notice that each of our bars are equal in width. Okay, it looks very presentable, it looks pleasable. Okay, it's not sloppy. Your parallel graph, okay, like we said, is just writing it from increasing to decreasing. So the most popular game that Pineview School has is tennis, with 35 members. Second would be baseball, third would be cricket, fourth is hockey, and fifth is chess, okay? So the only difference between your bar graph and your parallel graph is, your parallel graph is going to be written from increasing to decreasing order to show which items or which sports are most popular. Dot frequency graphs. The dot frequency graph displays the data on a rectangular grid. So things to remember, once again, make sure there's a title. Okay, I'm sure your teachers tell you this all the time. Make sure it's a title, make sure it's neat. Okay, provide names and scales for the vertical columns and the horizontal rows. Make sure each dot is aligned with the intersecting points on the graph. So our example we have is draw a dot frequency graph for the data, okay, on the table below. So if I were to draw a dot frequency graph for our snack items, which is chocolate, pizza, burger, and ice cream, and the number of children that have chosen those, okay, it would look just like this. So results of 15 students surveyed for their favorite snack items. So we had 5 students, okay, 5 students loved chocolate, 1 student chose pizza, 3 students chose burgers, and 6 students chose ice creams. So your dot frequency is very similar to your bar graph, but instead of drawing bars, you're just simply drawing dots on your graph. Okay, have you guys seen these before? You guys have worked with this before? Okay. So, a question we have here is Noah conducted a survey on sports participation. He created the following two dot plots to represent the number of students participating by age in soccer and basketball. Which statement about the given data sets is correct? So look at your two dot frequency graphs and your choices that you have here, and let's see which statement is true. Okay, which statement is true? So choice A says the data for soccer players is skewed right. Okay, the word skewed means it's a little off-centered. Okay, it means it's a little off-centered. So if we look at your soccer players graph, okay, we see it's skewed, but it's skewed left. So choice A you could eliminate. Choice B says the data for soccer players have less spread than the data for basketball players. Okay, so if you count all your data and you count all your dots, okay, you notice that choice B could also be eliminated. Choice C says the data for basketball players have the same median as the data for soccer players. Okay, now what is median? We talked about it in session 2. Your middle number. Okay, so is your middle number for basketball players, which is 9, okay, the same median as the middle number for your soccer players? So we know that's wrong. And choice D says the data for basketball players have a greater mean than the data for soccer players. So how do I find the mean? Or what is my mean? What is my mean? What do we think? Your average, right? So remember, to find your average, add up all the data that's given to you and divide it by the number of items you have. So choice D, okay, choice D is correct. Your mean for your soccer players is going to be 8.6 repeating, and the mean for basketball players is going to be 9.8. So choice D, the data for basketball players have a greater mean than the data for soccer players, would be correct. Now let's talk about line graphs, okay? Let's talk about line graphs. So a line graph represents changes in a specific item over a given time period. It's especially useful in charting the price of a share of stock, height or weight of a child, profits or losses of a company, okay? So just a couple things to remember. Make sure we have a title, make sure we have names for our axes, and very important, make sure we connect the plotted points in consecutive order to form the graph, okay? Make sure we're connecting them. So the example we have here is construct a line graph for given data which shows the average temperature of Washington for the calendar year of 2017. So we have all of our months, okay? We have all of our months, and in our months, okay, we have all of our data, the average temperature, okay? So if we were to draw a line graph, okay, we notice that January, the average temperature in January is, there it is 8 degrees Celsius. So if you follow January, it should be right around 8. For February, we were given 10, so we plot our point, okay? For March, we had 14. For April, we have 20. For May, we have 25. For June, we get 30. For July, we have 32. So you notice, okay, you can notice that in January, obviously it's a lot colder, okay? And as the summer months come along, our temperature is increasing. And then as September hits, from August to September, we notice a decrease. So it starts to get cold again, okay? So this is just an example of what our line graph should look like. The graph below represents a jogger's speed during her 20-minute jog around the neighborhood, okay? Which statement best describes what the jogger was doing during the 9th, okay, during the 9th and 12-minute interval of her jog, okay? So let's try to think about that. So we could definitely eliminate choice A, she was standing still. Because if she was standing still, then she would be at a 0 speed. So that could get eliminated. Choice B says she was increasing her speed. Well, from minute 9 to minute 12, it stays the same at 6 miles per hour. So we could eliminate choice B. Choice C says she was decreasing her speed, so once again, B and C could both be eliminated. Choice D says she was jogging at a constant rate. So from her 9th minute to her 12th minute, you could see that she's staying between 6 miles per hour. So choice D would be correct. She was jogging at a constant rate. Okay, she was keeping a constant pace. So choice D would be your answer. Picture graphs. Okay, picture graphs. I'm not gonna lie, I never liked picture graphs because I couldn't draw to save my life. So I was never a big picture graph guy. Picture graphs or pictographs is a graph which uses symbols to represent the quantity of the item rather than a number scale. These graphs are used to compare different items such as populations, numbers of cars manufactured, bakery sales, okay? One limitation of a picture graph is that if part of the symbol is used in the graph, it is difficult to accurately determine the value of its representation. So for instance, let's say we were talking about numbers of cars manufactured, and we were drawing a pictograph, and we were using mini cars as our symbols. If we said Ford creates 9.5 cars per hour, okay, you could draw 9 cars, but the half a car is kind of hard to representate, okay? So points to remember, once again, make sure we have a title for the graph, your names for your axes. Choose a simple symbol to represent the quantity of items being studied, okay? So if you were to use, let's say, populations, if you were to do a pictograph of populations, what would be something easy to draw? What do you think? A stick figure, right? So just draw a stick figure. Use simple symbols. Clearly label what the symbol represents, okay, and align the symbols in equally spaced rows and columns. So the example we have here talks about 4 branches of Party America, which is an online party store which supplies balloons for parties. Construct a pictograph for the sales of balloons per day. So we have all of our data, okay? We certainly don't want to draw 492 balloons for this graph, okay? We don't want to do that. You'll be there forever trying to draw your pictograph.
Like you could just make like 1 balloon equal 10.
You could do that. You could have 1 balloon equal 10, 25, 30, 40, whatever you would like to do. Okay, so it's more efficient to represent sales in terms of dozens of balloons. So we will let each balloon picture represent 1 dozen balloons sold. Now the chart would look like this. Okay, the chart would look like this. So we notice, once again, we have a label for our graph. Okay, our x-axis is labeled, our y-axis is labeled, and very important, we note, okay, we note that 1 balloon equals 1 dozen balloons sold, okay? So don't just draw your balloons thinking, oh, they'll know what I'm talking about. No, 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 make sure you label what each picture or each symbol represents. Circular pie graphs, you guys have dealt with circular pie graphs before, okay? Circular pie graph is used to show how a whole quantity is partitioned into various categories. It can be very helpful in visualizing budget expenses, types of questions on mathematics tests, and the types of books in libraries. So for each category, in a circle graph is represented by a sector of the circle. That's why it's called a pie graph. A sector is a portion of the circle formed by 2 radii and the included arc of the circle. The size of the sector is dependent upon the portion or percent that the category of whole. Okay, so to determine the size of each sector, determine the magnitude or size of the whole. So you need to know, okay, when dealing with circular pie graphs, you need to know how big a role one item or one category has on the entire graph. Okay? So, points to remember, title for the graph. Use a compass to draw the circle, okay? Make sure we use a compass. Once again, you don't want it to be sloppy. Use a protractor to measure and construct the angle for each sector. Label each category. The percent of each category may be displayed on each sector. So the example we have is 150 books were sold in a day. The details are as followed. So, what we did here, okay, is we know that total books sold was 150. So if we look at all of our books, okay, all of our books, and the amount of books that were sold in a day, the way to find your percentage is if you have 25 books sold of Magnolia Table, we have to find what percentage of 150 is that. So we do 25 over 150 to equal 1 over 6, or 16.667%. Okay, the degree measure of the central angle, the degree that we're going to use for this is 60 degrees. Okay? Yes? How do you know the degrees? So once you add up, okay, once you add up all of your percentages, you have to make sure that they equal 100. And then from there, you could say, okay, what's 16% of 100? Okay? And from there, you'll find out that your 60-degree angle would be the perfect amount on a circle or a pie chart. Okay? So using your percentage information based off of 360 and 100%, yeah. On the Regents, I think so. If it's better to just bring your own. Just bring your own, yes.
So, would you set it up as a cross product?
Yes, you could set it up as cross, yep. You could definitely set it up as cross product.
X out of 3, X over 360
Equals percent over, yep, perfect. Okay, so after we have all of our data, all of our percentages, okay, and we notice what degree we're using, okay, we could then make our pie chart or our circle chart. So we know Magnolia table was a 60-degree angle. Okay, Magnolia table was our 60-degree angle, so we can notice it right here. Oh, the places you'll go is only 6.667%, or a 24-degree angle. Okay, Warstone was 10%, the cast was 12, so on and so forth. So this is exactly how your circle or pie chart should look like. Okay, questions on these? Stem leaf plots. Have you guys dealt with stem leaf plots before? Yes? Okay. Stem leaf plots. Organizes the data in such a way that each individual value is displayed. So for each set of data, the stem must first be determined based on the numbers of the digits in each data entry. So draw a vertical line and list the stems in ascending order from the left of the vertical line. Write each leaf for the appropriate stem to the right of the vertical line, arranged in ascending order. If there are several leaves for a given stem, list them horizontally in ascending order. So, let's take a look at this.
Next video, we're going to learn about stem leaf graphs. A stem leaf graph is a method which is used to display data. The stem leaf graph groups the data with single data values. A group of 15 students were asked to record the marks they scored in mathematics. The marks of 15 students are 52, 66, 47, 35, 72, 66, 86, 72, 40, 65, 90, 96, 58, 65, and 81. Now, let's form the stem leaf graph from this data. From the data, we can see that there are 2-digit numbers. So, choose the digit in the 10th place as the stem and the units with 1 place as the leaves. To construct the stem leaf diagram, there are 4 steps. Step 1. List the stems starting from 9 to 3, one under the other, and draw a vertical line to the right. That is, enter the 10 place digits from the given data. Step 2. Write its leaves to the right side of the vertical line. Step 3. Enter all the leaves to the corresponding stems. Step 4. Sort the leaves in numerical order after each step. And now you know how to construct a stem leaf graph.
Questions on stem leaf graphs? So the example we have here is the age of 12 employees are as follows. Okay, so we have all of our data. The tens digit will be selected as a stem since every number contains 2 digits. In this example, the stems are going to be 2, 3, 4, and 5. Okay, 2, 3, 4, and 5. The digits following the stem become the leaves. In this example, the leaves are 0 to 9. So notice when we write our stems, Okay, notice when we write our stems, they're in numerical order. Okay, they're in ascending order. So very important. So now we could say, okay, we know one age of employee is going to be 26. Another age is going to be 27, 31, 34, 39, 42, 46, so on and so forth. So this is how stem and leaf graphs are shown. Questions? Box and whisker plots. Okay, box and whisker plots. There's a couple key points that we have to know about box and whisker plots. All right, there's 5 pieces. So the first piece we're going to talk about is your lowest value, which is going to be your minimum. So when you're given your list of data, the smallest value, the lowest value you have is going to be your minimum, which is going to be marked all the way to the left of your number line. The second, okay, is your highest value or your maximum. So the highest or the largest number that you're given is going to be marked all the way to the right on your number line. Now your box is going to be made up of 3 lines. The first line should come from your median or your middle number, okay? Your middle number of all the data that's given to you. Your first quartile or your Q1, okay, is going to come from all the remaining numbers that you have to the left of your median. Find the median of that group, okay? So the lower or first quartile is going to be 0% to 25%. Your third quartile is going to be the list of numbers that's to the right of your median, and you're going to want to find the median of that group of data. So to find quartiles, arrange the data in ascending order, identify the mean, which is Q2, for the set of data, for the set of values below quartile 2, find the median. This is quartile 1. For the set of values above your median, this is quartile 3. So the following are the marks scored by 20 students on the math test. So construct a box and whisker plot. So very, very, very important. I tell my students this all the time. Make sure you're arranging them from increasing order. You're not able to find the correct median by looking at all this data. Make sure they're written in increasing order. So since there's 20 values, the median is going to be located between the 10th and 11th value. So since we have an even number, we're going to average out our 2 middle numbers, which is 72 and 78, to get our median, which is going to be 75. So your first quartile is going to be the median values to the left of 75. So all the numbers to the left of 75, okay? Namely 52, okay? Because you're going to have another even amount of numbers. So average them out to get 52, 48, and 56. The third quartile, the median of the values to the right of 75. So all your numbers to the right, okay? So your 2 middle numbers on the right is going to be 86 and 87. Average them out to get a median of 86.5. The lowest value is 12, and the highest value is 97. The lowest value should actually be 18. I don't know why it says 12. It should be 18. I apologize. So here's what your box and whisker plot's going to look like. You compare it to, okay, you compare it to a number line. So you can do it vertically, okay, you could do them vertically, or if you want, you could do them horizontally. I usually teach them as horizontals, okay? So you notice we have a median of 75. So if I go to my median line right here, it should be right at 75. We notice that my minimum, okay, my minimum should be up here at 18, and my maximum we said was 98 or 97, okay? Your first quartile was listed at 52, okay? And your third quartile was listed at 86.5, okay? So once again, very important, you get all the data first and then plug that into your box and whisker plot. So the way I teach it is plot your minimum and your maximum numbers first with dots. Then for your median, your first quartile and your third quartile, draw them as lines. So that once you're finished with that, you should have 2 dots and 3 lines. Connect your lines to make your box, and then from the edge of the boxes, connect them to the dots to draw your box and whisker plots, okay?
In this video, we will learn about the box-whisker graph. A box-whisker graph is used to show details about data by using quartile values. Victor worked in a company for 20 weeks. The following are the number of hours Victor worked for each week. Let's find the quartile values. Rearrange the sequence in ascending order to find the median. The median is the second quartile value, and it divides the sequence into two equal halves. Find the median for the sequence in the left of the second quartile. Thus, we found the first quartile value. Similarly, find the third quartile value by finding the median for the sequence in the right of the second quartile. Let's draw the box whisker graph by using these quartile values. Draw a line and scale it from 0 to 30. Keep the dots above the numbers 0, 7.5, 9.5, 14, and 27. Draw a box connecting the dots that denotes the first and third quartile values. Inside the box, a vertical line is drawn through the dot that denotes the second quartile value. Join the dots representing the minimum value and the first quartile value. Similarly, join the dots representing the third quartile value and the maximum value. The shortest line segment at the left explains that the data is more dense at the first half of the data. The box denotes the range of the middle values of the collected data. And now you've learned about box whisker graphs.
Have you guys dealt with box and whisker graphs before? Okay. So Corinne is planning a beach vacation in July and is analyzing the daily high temperatures of her potential destination. She would like to choose a destination with a high median temperature and a small interquartile range. She constructed box plots shown in the diagram below. Which destination has a median temperature above 80 degrees and has the smallest interquartile range? Okay, so let's look at these box and whisker plots. Okay, let's see. Let's see which would have the best. So if we're following the median temperatures, we're looking for our middle line in our box, okay? That's what our median temperature is going to be. So our Ocean Beach one, okay? Our Ocean Beach has a median temperature of about 77 degrees, okay? For Whispering Palms it has 87 degrees. For the Serene Shores, okay, we follow it down, we're right about 78%. And for Pelican Beach, it's right at 85%. Okay? So now she's looking for a median temperature above 80 degrees. Okay? Above 80 degrees. So right off the bat, we could eliminate our top two choices. So we're left with Whispering Palms and Pelican Beach. The second thing that needs to meet her qualification is the smallest interquartile range. Okay, the smallest interquartile range. So the interquartile range that we have for Whispering Palms is right around 84. Okay, 84 to about 94. So 84 to 94 degrees. For Pelican Beach, it's about 83 and goes to about 87. Okay, so we could say that her best choice that has a median temperature above 80 degrees and the smallest interquartile range is actually going to be choice D, which is Pelican Bay. Okay, which would be Pelican Bay. Questions? All right. Our next example we have. Christopher looked at his quiz scores shown below for the first and second semester of his algebra class. So he's got his scores for semester 1 and semester 2. Which statement about Christopher's performance is correct? Okay. So we'll actually work on this one together. So for semester 1, okay, for semester 1, his interquartile range, okay, is actually going to be 91 minus 83, which is going to get me an 8. His median score, which is his middle number, is 88. His mean, or his average, is 86.8. And his third quartile is going to be 91. For a second semester, his interquartile range is going to be 9. His median score is going to be 88. His mean score is going to be 87. And then his third quartile is going to be 91. So, choice C says the mean score of semester 2 is greater than the mean score for semester 1. So the mean score for semester 2, 87, is greater than his mean score for semester 1. So we're looking to find the mean, the median, and his third quartile and his interquartile range for this sort of problem. Next, we're going to talk about histograms. So I mentioned histograms earlier in the presentation when we were talking about bar graphs. So histograms is used to represent data with a continuous frequency distribution. The distribution of the data describes the values it assumes and the frequency which they occur. So just a couple things to keep in mind. Make sure there is a title. Each class is represented by an interval on one of the axes. Okay, the other axis represented the number of values in the classes. Name and label the scales for your vertical and horizontal axis. And there is no space between each of the bars. So it's unlike the bar graph where the bars are separated from one another. So like I mentioned earlier on, okay, when we're drawing histograms, each of our bars are going to be connected. Okay? Very important to use frequency tables. Okay? To use frequency tables when making histograms. So, the example we have here is a sugar level in the blood of 20 patients has been recorded. The recorded data is as follows. So what we want to do, okay, is write it from lowest to highest, sugar level, and the blood are 80 and 198 respectively. So you're going to divide the range of values into equal interval or classes. So we're going to choose class 1 is going to be if you have an 80 or below sugar level in blood, which is less than or equal to 100. Class 2 is going to be 100 is less than sugar blood level, less than or equal to 120, so on and so forth. So count the number of pieces of data in each class. Okay, so in class 1, there's actually 5 people, there's 5 patients that have a sugar level in blood that's going to be higher than 80, but it's going to be less than or equal to 100. There's going to be 3 students in class 2 that have a higher sugar level blood than 100, but less than 120. Okay, so to draw your histogram, should look like this. Your y-axis is going to be your number of patients, okay, which is your frequency, and your x-axis is going to be your sugar level in blood, which is your intervals, okay? So if the midpoints of the upper sides of the adjacent rectangles in a histogram are joined by a set of line segments, the region obtained by joining these line segments is the shape of a polygon. That region is called a frequency polygon. So notice that our histogram, we have no spaces in between our bars, okay? Also, if we draw a line, okay, we could see that the region, okay, is actually going to be a frequency polygram. Have you guys worked with histograms before? Okay. And then the last topic we're going to discuss, okay, is cumulative frequency and polygon. So remember that a histogram is used to represent data with continuous frequency. The distribution of this data describes the values it assumes and the frequency which they occur. So a cumulative frequency histogram is similar, however, it describes accumulated data. So a couple key things to remember is each class is going to be represented by an interval, okay? Other axis represents the number of values in the classes. This axis is sometimes drawn on the right in conjunction with percentiles. Okay, make sure we name and label everything, and there's going to be no spaces between our bars again. So, the data that we have, the heights in inches of 10 kindergarten children are listed below. So step 1, the given data, the lowest and highest, okay, is going to be 40 inches and 49 inches respectively. So divide the range, okay, so have your different intervals. So your different intervals, so class 1, it's going to be height, that's going to be greater than 40, but it's going to be less than or equal to 42. Your class 2 is going to be heights that are greater than 42, but less than or equal to 44. For class 3, it's going to be heights that are greater than 44, less than or equal to 46, so on and so forth. So count the number of pieces of data in each class. So class 1 has 3, meaning there's 3 students, okay, there's 3 kindergarten kids that have a height that are larger than 40, but less than or equal to 42. So we notice there's 1 right here, 1 right here, and we have 1 right here. So 40, 41, and 40.5. For class 2, meaning we have 1 student, okay, 1 student that's height is above 42, but less than or equal to 44. Okay, that student is right over here to the left. So what our frequency is the amount of students that fit into the category. For the cumulative tally, create the following intervals or classes, okay? So step 5, count the number of pieces of data in each class, meaning class A, 3, there are 3 children with heights between 40 and 42. Class B, 4, there's 4 students with heights between 40 and 44. So just what I was saying, okay? The last tally number should match with the total number of pieces of data. Draw a cumulative frequency histogram using the information in the 4 steps. So once again, my x-axis is my intervals, okay, of all the heights, and my y-axis is going to be the number of children, okay, which is going to be my frequency. So we notice that there are 3 children, okay, that fit in the category of 40 to 42 inches, so on and so forth. Any questions about histograms or cumulative frequency histograms? Okay. In the upper right-hand corners of the adjacent rectangles of the graph are joined by a set of line segments. Okay, the region obtained by joining these line segments is the shape of a polygon. The region is called a cumulative frequency polygon. Okay, any questions on anything I've gone over today? Cool. So once again, last thing I'll say is thank you guys for coming and sitting in on this presentation. I hope you learned something today. All right. Also, just a reminder, if you go to learnamerica.com, they have practice tests, exams. The video will be up there of my sessions, other sessions that we do as well. Okay, and it's learnamerica.com. So I thank you guys for coming out on this Sunday morning and listening to the presentation. Thank you.
Expert teachers and educators at Learn America have created an online platform that helps students better prepare and improve performance in standardized tests in math and science. Step 1. Our unique methodology involves taking pre-assessment tests. Students take pre-assessment tests to determine their skills, knowledge, and readiness required for taking a course. Students are provided a detailed progress report at the end of the assessment to determine their strengths and weaknesses, and areas to focus on in order to achieve higher success in the course. Students access the courseware through the Learning Management System, or LMS, that is available anytime, anywhere, either through a browser or through the apps for the Android or iOS platforms. Students will have direct access to instructors, view any posted course announcements, and view a calendar of upcoming course events such as homework due dates, assessments, and so on. They may also download a learning report detailing any of their course activity, such as assessment scores, anytime. Step 2. Personalized learning plan developed based on the student's test scores in the pre-assessment test. The LMS includes an ebook for each course that provides theoretical concepts broken down by chapters and topics. Each chapter includes diagrams, graphs, or animated videos to provide visual demonstrations of the theory. The LMS platform has several features to make the learning process easy. Students can highlight important information, take notes, use the online calculator, and unit converter. Our expert teaching staff has created an extensive question bank that provides self-assessment questions in the form of quizzes after every chapter. These tests provide students a quick assessment of what they have learned in each topic or chapter. Students get to view the results immediately and provide an instant view of what specifically needs to be revisited prior to moving to the next topic. Step 3. Adaptive assessments and formative updates where students then experience a series of assessments. Formative assessments are configured to reinforce the essential concepts behind major topic areas and to prepare students for more rigorous assessments as they march towards exam readiness. The assessment results allow students a full 360-degree view of the courseware to reinforce the learning, and step-by-step detailed solutions to reinforce problem-solving abilities. Faculty will use the formative assessment results to further guide the students. The students are then put through a more challenging adaptive assessment process. Much like progressing through a video game's levels, students climb the competency ladder by mastering one concept at a time. The adaptive assessments culminate in a mock final exam covering the complete course. Step 4. Interactive moderated online forum. Students get an opportunity to participate in online discussions. Here, they can post questions and share information with other students taking the course, as well as faculty and teaching assistants. Step 5. Progress report and intense interactive review dialogues. We provide a detailed, personalized progress report to view course progress. Students may participate in faculty-led review dialogues. This is conducted either in person or over an online conference. Step 6. Ready review. Towards the end of the course, as their test approaches, students take a final summative assessment that details specifically what sort of outcome they can expect from their exam. With this assessment, students can dig deeper into what they need to know. Practice exams are available anytime and can be taken any number of times.